So I'm going to talk about Voronoi cells in certain random spaces. And I'll start with a definition in case anyone is not familiar. So XD is a metric space. And we have some points, let's say, x1 up to xk inside X are some given points. So the Voronoi cell of xi, I will denote it by ci. So this consists of all points z in X such that the distance of from z to xi is smaller than the distance from z to xj for every j. So that's the Voronoi cell. It gives you a partition of the space into cells. So if you have the Euclidean board and you have some point process, then you get some partition that will look like that into some convex shapes. Well, it's a bit difficult to draw, but you get some partition like that. And the question that we are going to consider is how big are these cells? So if you do this in, say, the Euclidean space, you can say for various point processes, you can say a lot. People have done a lot. I'm going to consider random spaces, and I'll say a few words about the motivation and why we came to study this. And this has to do with planar maps. And this is a side comment, and I will not give full definitions for the sake of time. It is the end of a day and the end of the week. But if you define the number of maps of size n and genus G, so if you are looking at a map of size n on the surface of genus G, then this is approximately, this grows like some constant depending on the genus, and then you have some exponential growth depending on the size of the map, and you have some polynomial correction, which is the size of the map to the genus minus 5/2. And these constants, the computation of these constants has been done in various situations using algebraic non-trivial analysis. And Guillaume Chapuy noticed that if you could understand the distribution of the volume of the Voronoi cells on this map, so if you take one of those maps randomly and look at a pair of points and look at the distribution of the Voronoi cells, if you could understand that, then this will give a much simpler derivation of these constants CG. And so there was a conjecture that he proposed. So if you take M is a uniform in this class of maps M and G, and you take X1 and X2 are uniform in the map, so you take just 2 points uniformly in the map, and you look at the size of the cell, say, of X1, and you look at it as a fraction of the map, then this converges as n goes to infinity in distribution to a uniform between 0 and 1.
So X1 and X2
are 2 uniform points in the map. So we take a random metric space, the map, with a graph distance.
So that's discrete now?
Yes, so it's a discrete, that's fine. We take 2 uniform points in the metric space, and we look at the volume of the 2 Voronoi cells. So this is the partition of the map.
In the 2 cells?
Yes, we have the 2 cells, C1 and C2. Let's just write this for the size of C1. So if you look at the fraction of the map that is in the first cell, this is asymptotically uniform between 0 and 1. And of course, you can run simulations of this, and you see that it's true. And
what's the role of X2 here?
X2 is the complement. So in order to define the Voronoi cells, you need to know the map and all the centers. So if you just know one center, you don't know what's the cell. So that's a conjecture, and in fact, this is now a theorem in the first case of genus 0. So, so this is a theorem due to Emmanuel Guiter. Unfortunately, the proof is one of the proofs Michael was talking about that only a mother can love. So it's so it starts with some very nice bijections due to Gray-Rogry-Mirmont, but you get into very heavy and difficult computations and much technicalities. In higher cases, this is open for higher genus. But there's even a more general conjecture. So if you take x1 up to xk uniform in the map, so now you have k cells, not one. So you look at the vector 1 over n times the volume C1 up to the volume of ck. So this is a vector of real numbers adding up to 1. And the conjecture is that this converges in distribution to a uniform in the simplex, in the k-dimensional simplex. And again, simulations strongly suggest this is true. But this is very much open. I think it's known that for k equals 3, it's known that the product of the 3 coordinates has the right expectation or something like that. But it's very much out of reach. But at this point, and if there are any questions, please ask.
And it sounds, does Poisson-Dirichlet distribution have anything to emerge from this?
So Poisson-Dirichlet distribution does connect to this in various ways, but and it comes up in the proof in the case of genus 0, but it's not all you need. So there's a lot to do on top of that. So it will also come up in the proof that I will show later.
What is actually the model? N. So what n number of?
N is the number of vertices in the map. So you take a map of size n.
And any face, any kind of faces.
Say triangulations or quadrangulations. It shouldn't really matter what kind of face you take. So I. This would give a more. If you understand this, it would give a more conceptual explanation of the CGs that doesn't go through a heavy use of generating functions. Okay, but at any point, Guillaume tried and couldn't prove this for maps. He said, well, let's look at other metric spaces. And if you look at the simplest metric space, if you look at you want something compact. So if you take something like a sphere, then it's not so interesting. If you take the sphere and you take 2 points, then the Voronoi cells will just be a partition according to some great circle, and you get half in one cell, half in the other cell. You don't get anything interesting. So the sphere is not so nice, but there are other nice metric spaces that we know, and I said, well, what happens if we do this in a random tree? So from now on, let's say that Tn, so this is a uniform tree of size n. And to be concrete, let's suppose that our trees are rooted. So we have a root. And let's work with plane trees. So there's an order on the vertices. So it doesn't have to be a bipartite tree. You can have any degrees, but you have a tree of size n. And we can also treat this as a metric space. And I should mention, I'm going to discuss this kind of trees, but actually, as we will see, it doesn't really matter what kind of tree you take. So any reasonable tree will do. And again, we have this tree. We are going to take two uniform points in the tree. So x1 and x2 are uniform in the tree. So suppose we take, this is one of them. Now the tree, because it's a uniform tree, then any point is equally likely to be the root. If you move the root, if you replace the root by a different point and just pull the tree upwards, you get the same distribution on the uniform tree. So we can actually assume that x1 is the root. And once you have those 2 points, you can partition the tree into the Voronoi cells. So in this case, you get something like this. So this will be C1, and this will be the cell 2. And again, you can consider the volume of the cells and ask the same question. And you run simulations, and you see that you get exactly the same thing. You get uniform, that the uniform fraction of the mass is in the cell of x1. So the main result that I want to tell you about today is the following theorem. So if x1 up to xk, so this works for any k, are uniform points in a uniform 3Tn, then we have exactly this result, 1 over n, the volume of the Ci converges to uniform in the simplex, in the k-dimensional simplex. So any questions about what we are trying to do?
Sorry, Ci are ordered in I?
Yes, they are ordered.
Does it mean that the total measure of overlap is 0?
Yes, it does mean that the total measure of overlap is 0. So of course you can have some overlap if you have, if this is x1 and this is x2. So you have the path between them, and if the path happens to have an even length, is this even? Let's see. Yes. So if it's even, if you have some subtree, if you have something large attached exactly at the center, then this will be in the overlap. But asymptotically, you don't get anything large attached just at the center. So you do have the path between x1 and x2, and you have some large trees attached to it, but the probability that you have a large tree just at the center goes to 0.
This is a yield, right, over the tree, over the points.
Yes, so this is an yield over the tree and the points.
And if you fix the tree, so do you have any improbability statements or something? I mean, for most trees?
No, it genuinely depends on the tree. It's not true for most trees. So if you have a tree that happens to be more compact, then you'll get a more biased distribution as a rule. If you have a tree that is very stretchy, if you have a diameter that is very long, then the tree is approximately a line. It will be roughly a line with small things attached to it. And it's an exercise to compute what happens on a line. So
And it's not the uniform.
it's not a uniform. Yes.
Those trees are unlikely.
Indeed.
I think he's asking if the most trees satisfied.
Well, okay. So you can quantify this. So the typical diameter of a tree is on the order of square root n. So the probability that it exceeds 100 square root n is some positive non-zero, and for those trees you get a different distribution. So there's no annealed state. There's no quenched statement that I think might hold. Okay, so let's say a few things about trees. The first thing that I will say is that it doesn't really matter what model of tree you take. So you can take a critical Galton-Watson conditioned on the size. You can take a uniform tree on n vertices, on n labeled vertices, so a Cayley tree. You can take these trees. So all of them. Yes, in the Galton-Watson, we want finite variance. For stable trees, the things are different. And the reason for this is that if you take the tree T of size n, if you take any reasonable tree of size n, and you look at the distance and divide it by square root n, then this converges as n goes to infinity to what is known as Aldous' CRT. So we have, let's just call it T and D. So this is the continuum random tree. So there is a limiting object. And so if you take the uniform points, then you need to look not just at the tree with the distance, but also the measure on the tree. So you have a tree and you have the uniform measure on this. So let's add here the measure, mu, which is the uniform measure on the tree. So the limit is the CRT, which also has a mass measure on it. And in fact, what we show is that in the limit, so if you take x1 up to xk uniform points, so let's change this from the uniform tree. So in the CRT, so no longer need to normalize. The probability measure is already normalized. So this vector is now equal to uniform. In distribution is precisely equal. So if you have this, then any reasonable tree that you get will converge to this. So that's actually the theorem that we prove. Now, in order to say a few things about the proof of this, I need to say a few things about what the CRT is and the sum of its properties. So I'll remind people of this. So the first thing to know, if you have a finite tree like this, a finite order tree like this, then you can consider the contour around the trees. Let's draw a larger tree. So we have a tree like this. Then we have the contour. We have the contour around the tree. And the contour, if you look at the distance from the root along the contour, then you get some excursion like this that starts and ends at 0. So this is the contour function of the tree. And you can conversely go from a function from a non-negative excursion to a tree by, you can think of it as just putting glue on the underside and squeezing, and you get back to the tree. And if you do the same thing with the Brownian excursion, so if you do the same thing with the Brownian excursion, then this corresponds in the same way to a continuous tree, which is the CRT. So you have some paths and you have branching. You have an infinite amount of branching. So what do we need to know about this? So if you look at the interval, so if this is an excursion of length 1, so the interval 0, 1 corresponds to the contour. So you have the contour around the tree like that. And Lebesgue measure corresponds to the standard mass measure on the tree. So that's a probability measure on the tree. And at this point, you can do something like this. So suppose we have 2 uniform points in the tree. So because of this invariance to rerouting, as I mentioned, we can assume that the root is one of them. So the root is 0. So that will be our x1. And then we take some other point, x2. And we want x2 to be a uniform point. So we take it at a uniform point along between 0 and 1. So x2 is maybe somewhere here. And once we have this, so once you have x0 and x1, Well, if you want to look at the Voronoi cells, you look at the path between x1 and x2. So the path you just split midway. And then you have all the small subtrees that are attached. Anything that is attached on the bottom half goes to the cell of x1. Anything that is attached to the top half goes to x2. Now, the path itself has zero measure. So again, I'm going to say various things about trees, and if you haven't seen them before, you'll just have to accept them. So the path itself has zero measure. All the measure is in the trees that are attached on the side. So you have some of the trees attached to the bottom, some are attached to the top. And at this point, you can start analyzing this. So you have this Brownian excursion, which we understand very well. We have, if you look at excursions above certain levels, then you also understand those. So you have various excursions here going up to x2, and then you have various excursions going down on the other side. And you have those excursions, and you want to know how much of these excursions happen below half the height of x2. And you can start computing the Laplace transform, and it's a somewhat messy computation. Let's say it's a proof that close relatives could love, not just a mother, but still a somewhat.
First degree cousin.
Yeah, well, let's say yes. So this works for 2 points. If you try to analyze this for more than 2 points, for 3 points, things become much hairier, and you're back to just the mother if you can finish the proof at all. But let me tell you a couple of more things about the CRT, which will give us actually a very simple proof in the case of 2 points. And this is a proof that eventually we can generalize. How much time do I have, by the way? When should I finish?
You have 20 more minutes.
20 more minutes. Ooh, that's very generous of you. So.
Okay, then 5 minutes.
That's even more generous. Right. So one thing that we have x1 and x2, which are the 2 uniform points. And we have some subtrees attached on top of this. So I'll draw them like this. So here are some facts that I will state. So given the distance between x1 and x2, the subtrees, the remaining subtrees have some masses. Let's write it as 1. So it's an infinite sequence of masses. It adds up to 1, so that's all the masses. And it has a distribution which can be written explicitly and closely related to Poisson-Dirichlet, but we don't actually need to know what is the distribution. It's a proof with no computations. So they are attached to the path from x1 to x2 at uniform locations. So if you condition on the length of the path, condition on the subtrees, then they are just glued at uniform locations, and also uniformly on left or the right. So each subtree is equally likely to be on the left or the right. That's very natural. In a discrete setting, it's almost obvious. You can move things around and you still have a uniform tree. So that's one fact. The second fact is that if you look at the sum of Si such that the tree I, let's call it T tau I, is on the left. So I look at just these subtrees that are on the left. So this, well, this is just this contains all the contour of the tree from x1 up to x2. So this is just equal to x2 minus x1, which is x2 since we assumed x1 is 0. Right? So we fixed x1 to be 0. So why is that? Well, the left part of the tree is exactly the contour from 0 up to x1. If you go along the contour function up to a point, then you just cover the left part of the tree. That's the construction. And this is uniform between 0 and 1. Because we said we take the point x1 to be 0, and x2 is uniform between 0 and 1. OK, so what do we have? We have some infinite sequence adding up to 1. On the one hand, the parts on the left contains each one of them with probability half. So if we condition on the sequence, and now we take each one of them with probability half and throw otherwise, then the sum that we get is uniform between 0 and 1. On the other hand, if we look at the Voronoi cell, so the Voronoi cell of x1 contains just the trees, so the brown trees are the trees that are in the Voronoi cell of x1. This also contains, if you condition on the sequence S, it contains each one of them with probability half. So it follows that the Voronoi cell has the same distribution as the contour from x1 to x2, and therefore it's uniform. So this is equal in distribution to the sum of SI, indicator that tau r is attached in the lower half. And this is equal to the size of the cell.
So I think I missed something. Why do you get the uniform distribution in the first part of the argument for the left side?
In the first part, so we have the Brownian excursion that encodes the tree. We take, this is x1, which is 0, and we take x2, which is uniform. So now if you want to know what is the interval 0, 1, the interval from 0 to x2, so this interval corresponds, so if let's make it in blue, so this interval corresponds to just the left part of the tree, like that. And right, and then you have the rest, which corresponds to the blue. So by construction, it's uniform. So that's the proof when you have k equals 2 points in the tree. So then we say, well, if it's so simple for 2 points, let's try 3 points. And for 3 points, what happens? So, OK, so let's start with the Brownian excursion. We take 3 points, 0, x2, and x3. And these 2 points are uniform on the interval 0, 1, so that we get uniform points in the tree. So the intervals from x1 to x2, x2 to x3, and x3 back to 1, which is the same as 0, these intervals give you a uniform partition of unity. So xi minus 1, so this uniform in the simplex. So that this part is nice. So what do these things give us? So let's draw the tree here. So we have here x1. Let's draw it slightly more skewed. We have here x2, and here we have x3. So, so this gives us the 3 parts of the contour, and this is where there's a slight problem. I was asked not to use the red, but there's also no green, I see, and so we only have 2 colors.
Orange works well.
Orange works well? Huh. OK, good. Huh. OK, so good. So we have one part contains all the subtrees that are attached. No orange? Yes, OK, so. Okay, so we're going to have to use our imagination. And we have, on the one hand, from x1 to x2, this contains, so you have all the subtrees attached on this side of the path from x1 to x2. So all of this, so x2 minus x1 is the length of the contour from x1 to x2. And similarly from x2 to x3 and from x3 back to x1. So these are the three contour lengths. Now, if you condition just on the subtree spanned by x1, x2, and x3, so the subtree looks like that. So you have a center point and three branches to x1, x2, x3. So each of the other subtrees, so you have some, so if you have Si, so these are the mass of remaining trees. So it's the sequence of masses. So each of those, so I'm going to condition on this sequence, and each one of them is attached at a uniform point and on a uniform side. So in particular, each of the subtrees has a certain probability of being attached into this contour. It has a certain probability of being attached into the second contour and a certain probability of attaching on the third contour. And similarly, if I know what is this subtrees, then I can also find the Voronoi cells. Because for the Voronoi cells, I just need to cut things midway between x1 and x2 and midway between x1 and x3. So suppose I have the length L1, L2, and L3. So suppose that L1, L2, and L3 are the length of the three legs here, from the center point to x1, x2, and x3. So if this point is z, so Li is the distance from xi to z, then what do we have? The probability that that a tree that Si is attached in the contour from xi to xi plus 1 well, the probability that I'm connected on the contour between x1 and x2 is L1 plus L2 divided by the total length, which is twice L1 plus L2 plus L3. So this is Li plus 1 over twice the sum of the Li's. Bye. And the probability that Si is attached in the cell, in the Voronoi cell Ci, well, this, if I know the three lengths, then I can compute this. And now it depends a bit on which is the shorter and which is the larger. But suppose we have this case where L1 is less than L2 is less than L3. So the length of the Voronoi cell, let's say of the cell of 2, it contains this segment, anything that's attached in this segment, which is half the distance from x1 to x3. So it's equal. So for I equals 2, we get L1 plus L2 over normalized. For L3, we get L2 plus L3 divided by the same factor. And here you get what's left, which is L2 plus L3 divided by the same factor. So if you condition, so what's the summary of this? If I condition on the three distances, L1, L2, and L3, then I get some partition. The remaining subtrees are attached in a random way, and we have some probability of being attached in the cell of 1, and cells of 2, and cell of 3. So we get some distribution on the three cells. On the other hand, we get some distribution on the three contours. But these distributions are the same. Right? So for the cell we have L1 plus L2, L2 plus L3, and L3 plus L1 with some normalization. And for the three Voronoi cells, we have the same thing. So Russ seems confused. No, good. What's the typo?
Well, you look at I equals 1 and I equals 3.
I equals 1. Yes, indeed. Yes. Better. Thank you. So we have some random permutation here, which depends on which of the LIs are larger. But because these things are exchangeable, it's all symmetric. It doesn't matter what permutation you take. So you get the same distribution on the Voronoi cells. So the volumes of the Voronoi cells, which are the sum of all the trees attached to these corresponding segments, has the same law as the total mass of the contours. And the length and the mass of the contours is uniform by construction, as we said here. So that's the proof for L equals 3. It's a bit more delicate than L equals 2, but still somewhat nice. How much time do I have? It was 7 minutes. Okay. So for going beyond 3 points, things become a bit more delicate. Because if I have 4 points, so the subtree spanned by the 4 points has some shape like this, and I could consider the condition on the different lengths. So I have 5 segments here. I can condition on the 5 lengths, and I could say what are the Voronoi cells. So I have some partition maybe here and here and here into the 4 Voronoi cells. And I can compute their lengths, and I can compute the length of the contours, contour segments, and it's not going to be the same things. So so we don't get the same distribution here. Or we don't get, for a given tree, we don't get the same distribution. So if I condition on the 5 lengths, it's not the same. What we do have, and at this point, I'm going to discuss the stick breaking construction, or I'm going to use the stick breaking construction without saying what it is. But if you're familiar with the stick breaking construction of the CRT, then what you can say, and this is fairly standard, that the subtree spanned by 4 points. So if you look at the subtree spanned by 4 points, including the lengths, then any partition of the total length into the 5 cells has the same probability. Or if you look at the density, so if you know that the sum of Li is some L, so if you condition on L, then any partition into the 5, into L1 up to L5 is equally likely. So you have the uniform density. And that means that we can, instead of looking at the actual lengths L1 up to L5, we could look at a tree which has exponential edge lengths. Because if we have independent exponential edge lengths, then it also has this property. And rescaling this doesn't affect the probability of being connected on various parts. All I care about really is that these 3 probabilities are the same as these 3 probabilities. And rescaling this skeleton has no effect on that. So what we work with is a tree with exponential edge lengths. And if you take a tree with exponential edge lengths, if you take this particular tree, which is what happens if you have 4 points, and you put 5 exponential, independent exponential edge lengths, so we switch, so we replace Li by some independent exponentials with rate 1. And now I look at on the one hand, I look at the vector of the 4 Voronoi cells, the lengths of the Voronoi cells, which determine how much of the mass is likely to be attached to those. On the one hand, I look at the vector of the 4 contours, which tells you how much of the mass goes into each of the contours. Then these 2 vectors have the same distribution. And this is proved by looking at what is the shortest exponential and starting to cut the tree at that point. And it's and I think in light of the time, I will not go over this in detail. But this has the same distribution, and consequently, you get the result for k equals 4. And if you want to go to k equals 5 or 6, then the same argument now works, and there's an induction on the number of points, with one extra fact that the tree itself is a random tree. So if you want to take, say 1, 2, 3, 4, if you want to take 7 points, then you get a random tree where the internal vertices have all degree 3, and we have 7 leaves here. And now you put the exponential edge lengths on that, and for this tree, the distribution of the contour, of the length of the contour from one point to the next, as the partition of the contour to the 7 segments, has the same distribution as the length of the Voronoi cells. So that's what's needed to get these 4K points. And that's the end of the proof of the theorem from before. So if there are questions about that, if not, then I can say a few things about further generalizations. But
so is it not true if you just take x1 to be 0 and x2 as this random point, and you just look at the tree attached to on either side of the segment between x1 and x2 in the Brownian CRT, is there no rescaling to say that that also has a distribution of the CRT?
No, it's not quite a CRT. It's a CRT with a certain bias. It's a CRT with 2 marked points. So you get a certain bias for depending on the distance between them. So it's not exactly, but. So let me just say, so at this point, we say, okay, so it works for random maps. It also works for trees. Where else does it work? So there's one space, one random metric space where this works for very simple reasons, which is if you take the complete graph. So if you take Kn with exponential edge lengths, so in this case, you can check that the Voronoi cells are exactly emulate a polyiron, and it's a simple exercise to check that it works. It works for the trees. It turns out that it also works on other spaces, and the spaces that we can currently do are the analogs of tree on any surface. So let me say the theorem. So same for tree on any surface, on closed, a compact surface with no boundary. So what is a tree? A tree is a graph that if you draw it on the surface, there's only one face. So it's a map with only one face, to be precise. So a unicellular map is the more precise definition. So if you have the torus, then a tree on the torus is going to have a cycle going around the torus in this way, and it will also have a cycle going around the torus in this way, like so. And then you have lots of small trees attached to this structure. So topologically, if you just draw it on the plane, the same graph, then topologically you get something that looks like that, with some subtrees attached anywhere. So it works, if you take one of those uniformly, it works. So this is basically a graph that is topologically a theta. So if you take a graph that is topologically a unicycle, just a cycle with finite trees attached to it, this still works. It turns out that this is the uniform tree on the projective plane. So a tree on the projective plane will have precisely one cycle. And it works in any genus, and okay, there are some further generalizations to maps with more than one face, which, if true, they might lead to a proof of the conjecture for planar maps. But this we cannot do yet. So at the moment, we can do this for unicellular maps on any surface. But I'll stop here and thank again the organizers and Ras.